So to close us out in our session here on propulsion, we're going to hear from Les Johnson. He's the solar sail PI for the NASA Near-Earth Asteroid Scout mission, the formulation manager for nuclear thermal propulsion at NASA Johnson Space Flight Center. He's done a whole bunch of work on solar sailing over the years and too many cool things for me to list off right now. And he also happens to be a best-selling science fiction author. So let's welcome Les.
I have to correct the record, or the folks back home at the Marshall Space Flight Center might get upset with me for having Johnson claim me. No offense to my colleagues from Johnson. Yeah, I'm Les Johnson. I am the solar sail PI for the NEA Scout. And I have to tell you, after seeing all the beamed energy presentations today, which I have studied in my career and I'm a huge advocate of, I almost feel like I'm going to be the stick in the mud. Because I'm going to tell you where we are today with solar sail technology, which is actually quite amazing considering where we were when I started my career 28 years ago. And I also want to give a shout out to science fiction because I was inspired and first heard about solar sailing from Larry Niven and Jerry Pournelle's great novel, The Mote in God's Eye. If you haven't read that, it's a bit dated, but it is an awesome novel about an alien invasion with laser sails. So it was inspiring to me, and as a physicist, to actually get to work on solar sails has been exciting. I am at the Marshall Space Flight Center. Today's talk will be talking about the state of the art of solar sails and what I consider to be a worthy competitor and a pretty promising technology called electric sails, which Bob Zubrin gave an introduction to earlier, that we're actually testing at NASA Marshall and looking forward to a flight validation sometime in the near future. I'm not going to be talking about laser sails. I'll be talking about these mundane solar sails, just using solar pressure and sunlight for thrust. But there's a lot we can do. And one of the things that I would like to see enabled maybe before I retire is this interstellar precursor missions to take us out to the solar gravity lens so we can do some pretty exciting exoplanet research and explore the nearby interstellar medium. And I believe the technology to do that is within our grasp with solar sails. And to justify that, I'm going to tell you this has been a great decade for solar sails. The decade began in 2010 with NASA's NanoSail D from the Marshall Space Flight Center in collaboration with the Ames Research Center. It was a simple deployment demo in low Earth orbit of a 10 square meter solar sail from these new technology CubeSats at the time. It was a 3U CubeSat, but it was deployment only. We were totally skunked by the Japanese, who launched Icarus. The interplanetary kite craft accelerated by radiation of the sun was a very large solar sail, a small sat sail. Almost 200 square meters, and they demonstrated the first interplanetary use of solar sails. And for those of you that study Greek mythology, just ask yourself if you would have named your solar sail mission after Icarus. I would not have done that. Daedalus might have been a better name, but that was already taken, right? Shortly thereafter, the Planetary Society took the same kind of idea of a deployment demo and increased the area that you could pack a sail into a 3U CubeSat, and they successfully deployed and got this great photograph, which Bill Nye calls the money shot, which is aptly named. It's a beautiful photo there in the minute. But it was also in the middle. It was also a deployment demo and didn't go anywhere. Since then, we've had the Canadians with the CanX-7 in 2016, which was a less than 10 square meter drag sail, solar sail-like deployment, and the University of Surrey in the UK with their inflate sail in 2017. I had the privilege of being a co-I on that flight. So there's a lot that's happened. This year is going to be a busy year. You've probably all heard that the Planetary Society is going to fly the second light sail. We'll actually do solar photon maneuvering in low Earth orbit, and they will be having company. CU Aerospace and the University of Illinois at Urbana-Champaign have manifested their CubeSail, which is a 20 square meter solar sail. It's a thin strip, a technology that is a different kind of configuration for a solar sail, but they also are going to fly this year and demonstrate orbital maneuvering with a solar sail. But the mission I want to tell you about is the one that I'm leading for the sail development for, and that's the NASA Near-Earth Asteroid Scout Solar Sail Project, and that'll be the United States' first interplanetary solar sail, where the solar sail is the primary navigation system to take a small spacecraft with a camera to do a slow flyby of an asteroid and actually accomplish mission science. We are a 6U CubeSat form factor, but it's a 6U CubeSat form factor in name only. We're 10 centimeters by 20 centimeters by 30 centimeters and have almost nothing inside that's common with any CubeSat that's flown currently, because CubeSats to date have primarily, if not exclusively, been in Earth orbit. And as a consequence, they have very different radiation environment, different ways of communicating. They don't have the long life requirements that we will have for a 2.5-year mission to an asteroid. So we basically have an interplanetary spacecraft built by NASA JPL, crammed into this little small footprint with the solar sail that we've developed at the Marshall Space Flight Center as its propulsion system. Our sail is 86 square meters, and unlike my positron dynamics counterparts today, I do have samples. I'm going to pass one to each side of the room. This is the same material from which our solar sail is made. It's a polyimide, it's a plastic. It's aluminized. It's about 3 microns thick. You can tear it if you try. Please do not try. But just by handling it, you shouldn't damage it. So I'll hand one to each side of the room. And if you would, just make sure I get it back before I go home today. You won't annihilate, I don't think. So the NEA Scout. How is this going to work? We are a secondary payload on the first flight of NASA's Space Launch System. Why is that? Because it's getting us on Earth escape. Solar sails are low thrust. We don't want to spiral out of Earth orbit. We want to be on escape before we deploy. We've gotten a ride from NASA SLS. We're going to be kicked off the spacecraft when the Orion has already been sent on its way to the moon. We're going to go out into space. We have some cold gas thrusters to stabilize, to stop tumbling. We're going to go into an elliptical lunar orbit and deploy our sail at that point. Now, how big is this system? Get a sense of what 86 square meters is compared to our spacecraft. You can see here on the bottom right is our 30 centimeter tall CubeSat. And then there's my shadow, a school bus, and the size of the sail. The sail is deployed from the CubeSat using 4 booms that are about 7 meters long. The material is folded up into strips and it's spooled up on a spool. And we have a motorized deployment of the sail, which will take about 20 minutes. Now, I have pictures coming up of our engineering development unit. We're actually doing our full-scale flight sail deployment, try saying that 5 times quickly, on the 26th of April in Huntsville. Then we're going to package it up and send the spacecraft this fall to the Kennedy Space Center, where we'll be awaiting launch. So we're not just a planned mission. We're just about finished building the whole system. There's a picture of the team after one of the deployments of our engineering sail, a successful deployment. You can see in the centroid here is where the spool that will fit into the CubeSat, and underneath the fabric is where the booms are that deployed the sail. You can get a sense for what the whole scale of this is. This is a picture, a mock-up of the CubeSat with its solar panels deployed that we used at NASA Day in the Park in Huntsville. In the middle there are the booms that we use for the deployment. Bottom is the spool, and on the right is basically what happens when you take the sail you've deployed and you haven't quite repacked it yet, and you just have to get it packaged up enough so that you can travel back home to spool it up on that little spool. This is our flight profile. We are going to be ejected from the SLS. We're going to go into lunar orbit to deploy the sail. We have to learn how to sail. And one of the things that I found coming into the solar sail field many years ago is I was enamored with getting bigger and bigger sails that are lighter and lighter weight, because we obviously need those for more aggressive missions. It is very difficult to envision flying those right now, because on the NEA Scout, just to give you an idea of how difficult flying these are, if we are off more than a few millimeters in managing our center of mass versus our center of pressure over a 2-year flight time, we will lose control of the sail. Okay? And the biggest challenge we've had has not been building a large sail, it's been learning how to control it to fly it. And so when the rubber hits the road, I learned that that was going to be a bigger problem. I thought our biggest problem would be deploying the sail. It's actually going to be controlling the sail. But we will learn to fly it. It's a low-thrust system. We've got a couple of years before we reach our target. And we're going to do a slow flyby of asteroid 1991 VG. We have a camera. We're going to characterize what this asteroid looks like. So it's pretty exciting. You can see here the system performance characteristics of the solar sail. Our acceleration is 7/10 of a millimeter per second squared. Pretty small, but it's constant. I will say that we came real close to being able to work with the Planetary Society to actually put a ground-based laser on the light sail and demonstrate beamed energy propulsion. We actually had a lot of the agreements in place with the people who have such things, but the schedules didn't line up with the availability of the laser in the Planetary Society's launch schedule, so that is not going to be done. But I will tell you, if we serendipitously have another sail in Earth orbit anytime in the next 5 to 10 years, come talk to me. We might be able to demonstrate the first Earth-to-orbit beamed energy propulsion of a laser sail, because we've located some assets that could be used to do that. I am an interstellar advocate. In another hat, I'm part of the Tennessee Valley Interstellar Workshop. My passion is to go to the stars, so of course, being a NASA guy, I have a roadmap of how we're going to do that. And actually, this roadmap is not my own creation. I've adapted it, but we've stuck to it. On the bottom left corner, you can see the first sails we thought we needed to demonstrate on the order of 10 square meters. Then we want to go up an order of magnitude in area to about 100 square meters. Turns out the NEA Scout is approximately 100 and could have been if we knew when we started what we know now about the packaging efficiency. If we go to composite booms instead of metallic booms, I can easily see us building a 1,000 square meter sail or larger, 1 to 4,000 square meter sail today. Say less, take your team and go. We could do that. And I'm confident as we're learning how to build that largest sail, we'll make the transition to building the next scale of solar sail, which is on the order of 10,000 square meters, which is what we need to enable some of these interstellar precursor missions with rapid trip times to beyond the heliopause. I know Lou Friedman will be glad to hear that. That's one of the things he's been an advocate of for years. And then as you go larger and larger scale, you get to the laser sails. I do want to give a shout out to the fact that I was very dubious about how we would possibly build sails that are tens of square kilometers in area. What material could we possibly have that's light enough weight to do that, to survive the stresses? That material exists today. A Nobel Prize was awarded for its discovery in 2010, and that material is graphene. We don't yet know how to make big sheets of graphene, but it has all of the right characteristics for extremely large, lightweight sails. Greg Matloff has written papers about how these could be used, and I can now see how this roadmap might actually be implemented. It's a matter of taking that material science and going from millimeter scale graphene samples to larger and larger samples, or finding ways to knit them together so that we can build these large solar sails and potentially large laser sails. Very briefly, I want to mention the electric sail. This is work that's happening at NASA Marshall based on the work of Pekka Janhunen, who is the inventor of this in Europe. He is a part of our team. Mr. Bruce Wigman had phase 1 and phase 2 NIAC to work on this, and we've continued to advance the technology of the electric sail with internal research funds at Marshall, and are carrying it forward in hopes of getting additional funding to take it to the next level of performance. In the interest of time, since I've only got about 3 minutes, and there's been an introduction given to how the E-STAAR works, let me just tell you what a system configuration might look like and give you a picture of the TRL. Now, in my previous life, before I started working on sails, I was a principal investigator and a co-investigator on electrodynamic tether propulsion systems. We flew some in low Earth orbit, and believe it or not, most of those were successful. I can have a discussion with folks about that. When you don't succeed at one, that's what people remember. But tethers have actually had a pretty good history of success. But an E-STAAR doesn't work in Earth orbit. It works in interplanetary space, and you deploy long, thin wires, put a positive voltage on them, you repel solar wind protons, and you can get thrust as a sail. Now, the reason this works so well, and we believe that it works well, and we've actually tested it in subscale tests in our plasma chambers at Marshall, is that it is a virtual sail. You put the voltage on those wires, you have an electric field around the wire, which gives your interaction region with the protons more than just the diameter of the wire. Now, the effective radius of the electric field is driven by the plasma density in which you're deployed. Well, at 1 AU, it turns out 6 kilovolts around these wires has an effective interaction region with the plasma in the solar wind of about 66 meters. So around each wire, you have a 66-meter virtual sail. Now, what's interesting is this, as the solar wind protons interact with that and repel the spacecraft, you are collecting electrons. You have to have an electron gun or some other way to get rid of that current on your spacecraft, or you will become charge neutral. But as the sail is deployed and moves away from the sun, unlike a solar sail, the thrust does not drop as 1 over r squared. The solar wind density continues to drop as 1 over r squared, or approximately. But what happens when that occurs is the virtual sail size expands as the plasma density drops. So as you have the 1 over r squared decrease in the density of the solar wind and the source of your protons, your virtual sail size increases, and it can get out to over 100 to 180 meters as you get further out from the sun, which means the thrust on an electric sail, in theory, will drop as 1 over r versus 1 over r squared. What that allows you to do is to get characteristic accelerations of 1 to 2 millimeters per second squared And on the same size spacecraft as some of these mission concepts we've looked at with the solar sail, you can actually get much faster trip times on a one-way trip out of the solar system. Now, do we have all of the kinks worked out of this? No, we don't. Steering is an issue. We're wrestling with that currently. People question, how do you deploy these long tethers? We've done it before. We've done it in Earth orbit. This is a system that we think you can do that and deploy kilometer-length wires. We've done high-voltage systems in space. At NASA Marshall, our space plasma physicists have done some lower density plasma modeling. We can't do 66-meter virtual sails in small vacuum chambers. So we've done some lower voltage, lower plasma density measurements. There's a model we've worked with the University of Alabama in Huntsville, done some PIC code modeling, and we think we've got a handle on how this scales up to to interplanetary performance and have some pretty good data to back that up. These are just pictures of some of the plasma chambers that we've used for the testing at Marshall. We also did a pretty thorough technology readiness level assessment as a technologist, but also someone who has to fly things. When someone tells me they're at a certain technology readiness level and ready to go, I'm inherently dubious, mainly because technologists, shock of shock, overestimate their readiness for things. So we had our experts who are not part of the team look at each element of the e-sail and give their assessment of where we were on the NASA technology readiness scale in terms of flying these. And it's fairly high, although not quite high enough yet for flight validation. So we're trying to knock down some of the problems we have and get this system ready to fly. So with that, I will conclude. I'm out of time, and I know we have to hand things off to the panel. So thank you very much. Oh, we have time. Okay. I don't escape unscathed. I saw the clock go to 0, and I thought I'd get away without questions. So, yeah.
Thanks. A great talk, Les. Real briefly, Brian Gilchrist and I, University of Michigan.
I know Brian very well, yeah.
Yeah, so he and I worked on a project that was analogous to this for DARPA about 10 years ago. And we found out you don't really need an electron beam. What you need is simply a power supply and to ground one end in the plasma. So you essentially produce the potential on the spacecraft by virtue of the power supply separating the charge.
Okay.
So I wondered, is this an architecture that could work for your system, or do you actually need that beam for some specific reason?
Could you repeat the actual question?
Yeah, so could that architecture work in your e-sail setup, or do you need the beam for some other reason?
No, you don't need it for another reason. It's really just to maintain the bias on the wires. It's really to get rid of those pesky electrons. So if there's a better way to do it, we're open to looking at that.
At least another way.
Awesome, good. I'll talk to Brian. Turns out we have our tether team still tags up regularly, so I'll make sure I ask him about it when we next chat. Certainly. I don't know who has the mics, so yeah. Hey, Jim.
So have you looked at micrometeorite impacts and how clean they go through, and at what velocity do everything fall apart?
We get good. That's a good question, and we get that all the time for the solar sail. It turns out when you look at micrometeors, they're traveling really fast and they're small. When they hit the sail, they basically poke a little hole in it, and that's about it, because they don't have much time to lose energy and deposit heat. And the rapid deposition of heat is what causes the damage, because that quickly expands and it's like a bomb going off. If that same micrometeor hits our spacecraft, mission over, right? But hitting the sail, we've actually done modeling, and we did some hypervelocity impact tests on different sail materials, and it makes it just a tiny hole. We built into our spacecraft our thrust model for the sail. Due to losses from tears or holing as we fly, we can lose up to 15% of the area and still meet our mission requirements. And we've also built into the sail ripstop, like on a parachute, so that if we have an unexpected tear, it won't propagate. So we aren't going to get a tear that goes all the way across the middle of the sail. So every meter we have ripstop, and we can sustain up to about 15% loss of area, but we don't think the micrometeors are as much of a threat, actually, as a tear. Because handling this material and folding and all of the G's during launch and going from atmospheric pressure to no pressure and having pathways for all the air to get out of the folded sail, all those things are a much larger risk to the sail, I think, than the actual risk of micrometeor impact. But we figured out how to do it. We've actually done rapid ascent vent tests to make sure that the sail didn't billow up during the launch segment. So we're actually out of time. Okay.
So let's thank Les again.